So let's start. So first, I talk about Martin. Martin Haas studied architecture in Stuttgart in London. He worked for Danish architects from 1995 to 2012, and from which he did last 6 as a partner of Stefan Benisch. He worked on projects in Germany as well as international projects in Dubai, Italy, and France. And you worked also, I've seen that in a river park project in Pittsburgh, yeah, and for buildings in Paris, for the Unilever headquarters, and the Marco Polo Tower in Hamburg. In 2012, Martin founded Haas Zemrich Studio 2050. Maybe later on you explain what 2050 means. And this office, we know very well, I know very well, Thomas is working on projects in Germany and abroad. And Martin focuses on the development of innovative, sustainable architecture. Also, Martin is a co-founder of the DGNB, which is the German Sustainable Building Council, and where he's a board member and since 2013, vice president. Martin has been a visiting professor at the UPenn in Philadelphia and also at the University of Sassari in Italy. Thomas Auer, is that right? Pronounce it correctly?
Probably yeah, not. I think you're close.
I'm close. So Thomas studied process engineering at the University of Stuttgart. And then since 1984, I think you joined Transolar, right? And your CV says you dealt extensively with issues relating to the energy efficiency and user comfort of buildings within the framework of your role at Transolar.
Did you say 84?
94.
1994. I'm not that old.
Okay. I think you're partner since 2001 at Transolar or Transplan, right? So Thomas held visiting professorships at the University of Kassel, the École Spéciale d'Architecture in Paris, and between 2001 and 2008, he had a teaching assignment at Yale University. Since 2014, Thomas is a full professor at the Technical University in Munich. Okay, and now I think, without further ado, I would like Martin to start the lecture.
Okay, I do. Trying to solve the technical issues. Do you see my screen?
Yep. Yes.
Okay, it works. Okay.
Sorry, before we start, maybe everybody could mute the mic, but I think you did already, so that Martin would not be interrupted. Okay.
No, you can interrupt at any time you want. So, guys, first of all, thank you very much for the invitation. Thank you for organizing everything, Thorsten. It's a pleasure. And quickly, I want to speak about the office, what we do, how we approach, and why, or why and how. And Thorsten asked me about the 2050 thing, and the 2050 in our name, Studio 2050, is to remember ourselves that in 2050, all the governments labeled the year as the year when we should have exceeded the carbon neutral status of the society. So I think it's a big challenge. It's only 30 years left, and if you now hear about the issues we have to solve to focus on this aim, you will know how little time we have left to proceed a carbon neutral future. So 3 partners, the bottom right image, David Cook, Stefan Zemrich, and myself. We have roughly 30 architects here in Stuttgart. We have a branch in Shanghai, which developed out of a former student I had in Pittsburgh. He worked in the office and then went back to China. So we work internationally on sustainable architecture. So, and when it comes to sustainability, it's a bit, for me, a very weak term of something big. I think if historians look back to this time of this period, they will realize that we are living in a change of eras. So a certain period come to its end and a new one is going to start. We have so rapidly changed society issues. We stay longer healthy. Getting old doesn't mean that you get retired. We have technical developments which allows us to work from every place. We don't need to segregate the city anymore between offices, living areas, and we want to work and live in a healthy environment, and we want to stay in harmony with the nature. And we have to solve the issue for 9 billion people on the planet. So we want to have all these comfort qualities for every person on our planet. So I think it's a big challenge we are dealing with. And I think you guys, the next generation of architects, will develop also what does that literally mean to our architecture. So we have to transform the way we worked and we perceive architecture in this tremendous way. What we do is most likely too little. I think we focused in the recent years just on solving our energy issues. So we generated more efficient buildings, but we haven't asked ourselves if this building in general, if this single house is the right attitude for this kind of a society, or if we have to challenge the building itself before we transform the energy consumption in a better way. So these big questions we are asking, I think, is something we have to look more deep into it. And when we talk about solving the big issues of resource consumption, we have to address effectiveness. So we have to, and that's showing this image of a train in India. Nobody wants to travel like that, but the energy consumption of that train, for example, is very high. Does have a high effect. So it transports many people. And if you compare that with a high-tech train in Germany, where only a few of persons sitting in, the effect of this high efficient train in relation to people is too little. So what does that mean for architecture? It means that when we talk about architecture, we have to address first that it should make sense to build the building, and it should provide usages from as much as possible persons as you can consider 24 hours a day, 7 days a week. So if a building is really used like that, then it made sense, and then it was worth to construct it. And that's the effect of our buildings. The first resource we have to talk about is space itself. We have one planet. We have only 2,000 square meters per person if we talk about 9 billion people on the planet. So we have to condense, and we have to use as much, or we have to use as little as possible of space to provide as much as possible quality to people. The building of New York, it's a very high efficient city. So, and if you compare the energy consumption of that little store here in relation to the people, which it provides an attraction to, maybe the energy consumption is much better if you compare it to a shop which is high efficient but doesn't attract so many people. So space, in terms of usage, and time is for me a criteria for developing new architecture. And if you solve the first questions for a building, that it makes sense, it provides much possible attraction to many people during for the whole day, then it comes to how you realize it. Then it comes to the materialization questions and how to use as little materials and to deal with the resource of materials quite well. I want to show you what that means. So we were charged, or we were asked to redevelop this former industrial site in Stuttgart. And in all these buildings, which were asked to be demolished, there's so much embedded energy installed that it makes sense to question first and foremost if it makes sense to deconstruct or not to keep the building, to keep the structures and to keep the embedded energy and to gain extra values into that site. So what we did, we overplanned the existing and redensed it and searched for new qualities by using all the roofs, using every square meter of spaces in different manners. So a square meter of kindergarten place could be used for the elderly people in the afternoon hours, that we have a lot of shared communities, shared usages, to have a 24-hour, 7 days a week used architecture all the way through. And if we add on new structures, we certainly do that in a way that the materials are better dealt with. So we use then wood or renewable construction materials. And all the rooftops are there for greenery, for food production, for microclimatic issues, to develop a better way of living in this dense urban environment. Embedded energy, the usage of materials, the synergies of different structures, all that needs to be considered. And you can guess that it is a very complex approach, and therefore I'm happy that I was asked by Thorsten and I can share my my lecture with Thomas, because I'm very strongly believe in the integral planning approach, which means that as an architect, that's a bit too much. You can't solve all these aspects as a single person. You have to work in a team with a couple of experts. And I very much appreciate this approach, that we cooperate from the very beginning with Thomas or with Thorsten to think all these new innovation approach for architecture from scratch. As I started my lecture, there is this kind of different criteria we dealt in the past about efficiency. We dealt at the very beginning only with the energy factor. Then we asked ourselves, can we reduce the amount of water? Can we reduce the amount of material embedded in the buildings? Can we reduce the amount of space we use? Can we reduce the mobility, or can we work with a more efficient, more sustainable approach into mobility? That's the first, how do you say, the balken? Thomas, give me the word for that. That's the first phases of this holistic approach into sustainable architecture. But when it comes to a carbon neutral future, we also have to address the way we live. So it's not anymore anything we can plan. It's also the way we share, we deal with the structures. It's the question how much, where the food is coming from, how do we deal with our travels, the consumption of materials. So, and there you see easily that when we talk about a new approach to a carbon neutral future, it's also a question of the ethics. It's the question of how we can steer our social environment in a better way. So it's a big picture. And I think it's very good time to become an architect, because as I said, I think it's great as an architect, you're a bit a conductor in a team, so you can steer a couple of these things. It's not about designing spaces. You develop areas where people live. So you develop a life pattern for the persons, and therefore you also influence the way people treat their nature and people treat themselves. How we approach that when it comes to a building. So we were lucky in a submission for a competition asked by the Guggenheim Foundation in Helsinki to team up and to finalize in the last round of 6 architects. And there we searched first the possible dimension of a building at the site at the harbor front of Helsinki, because in the harbor front of Helsinki, the Guggenheim Foundation asked for a new museum, and they reserved a huge part of this existing industrial harbor. We said, does it make sense to make that building like a museum, which is also a 9-to-5 usage, or would it make more sense to shrink the place for that museum and allow the city to grow in future in different ways, because nobody knows what the future is asking for. So maybe it makes sense to shrink the place for a museum to allow the city to develop in other ways in the future. So we also searched together with urban planners for the need of additional features in the city. So we said, what kind of qualities can this museum provide beside being a museum for art? And therefore we looked into the event calendar of Helsinki over a year. And we realized that it would be an additional quality if we could address an open public space accessible for everybody, not only for the museum's visitors, a public place which is sheltered against the strongly easterly cold winds in Helsinki. It's quite of a cold place in winter times. They hardly have sun, so they celebrate the spring period when the sun is coming back. So therefore we said it would be great if we could provide a place where they can celebrate the beginning of the spring, have a sheltered outdoors area with a lot of solar hits and celebrating the light as a quality, because light is a missing quality in that city. And there we focused with our design on shaping the museum in this highly in tower structures to shrink the footprint of the building, and then the towers themselves, the single tower spots, we modulated in a way that we have solar hits through these towers into the public space in the middle of that solar henge. So you see it here. And then we said, okay, we produce this place, public area, a place for gathering, for interaction, and we generate a kind of a chandelier in the middle where solar hits can celebrate lighting conditions, allowing for these kind of situations. That's an image, 21st of March, the beginning of spring, where a festival of sun could happen at that place. We searched for different qualities we can provide beside the museum. So we asked ourselves, what would we do spending 24 hours around that building, providing viewing platforms. We had a garden next to the museum, providing extra spaces. That the garden was an area where the city could then develop differently in future. So it was all about reducing the resource of space, maximizing the usages of that building. And with that, it came to an approach that we wanted to develop towers out of wood. We worked on a very innovative wood structure together with Thorsten and his team. And we wanted to show the society that a 45-meter high wood tower is possible. Inside the museum, movable platforms allowing artists to reshape the areas, because I believe that I'm an architect. I have only one brain, so it would help to ask artists to change the way the room layout would be over the time and year, to provide as much as possible different room atmospheres. It would be great if artists could tell me that the platform for their exhibition is on level 1, and for the next exhibition we want to have a more small space. That was part of this vertical white cube or wood cube, providing an extra venue for exhibition. So when you solve the question of it makes sense, you produce a space which could be in use for different persons. When it comes to materials, we also realize that natural materials, they have two positive effects. The first certainly is we save resources, but the second one is that they generate an emotional link to the people. People like the natural materials. They know them from nature. It's a very old, basic kind of relation you have with all the elements you see on a daily basis. And this emotional link helped very much that people appreciate buildings. And I think for a sustainable approach, durability is also a very important aspect. And durability means that people like the buildings and people want to keep the structures for a long period. And that's also something we shall not forget, that natural materials can provide this emotional link. When we develop houses, we ask ourselves, first and foremost, what would we do if there wouldn't be any energy at all? It's a very simple approach. All architects, the last 2,000, 3,000 years worked like that. So, but we forgot all these passive measurements about orientation, the right placement of a building, the amount of windows we need to have to gain daylight, but not solar hits. What does it mean to protect against the rain? And that is the new simplicity we very much like to approach with. So we still live here in Europe in moderate climate situations. So the span of a year where you can use a house without any energy is probably 75% of a year or 80% of a year. So the gap where you need to have heating or cooling is quite little. And therefore it's, I think, more intelligent to develop first a very passive, simple, basic structure which deals with the microclimatic conditions best. And for the gap, the rest of the year, you need to install high-tech. The high-tech, you have to acknowledge, in the moment where you install it, it's outdated. It's like buying yourself a cell phone, you go out of the shop, in the moment you go out of the shop, it's outdated. So therefore, high-tech and every technical element in the building should be additive. It should be something which is simple to be removed, could be reinstalled, could be gained better in future. Therefore, never consider technical features as a crucial element of your structures. I think that's also very important, that you can perceive a building which could be durable for a longer period. So that leads us to Alnatura, the building we want to talk about, because all these aspects I talked were embedded in this approach. We had a...
Ja. Vielleicht kannst du die Einstellungen unten beiseite schieben. Die sind ein bisschen im Bild, nicht schlimm, aber wäre besser. Entschuldigung.
Okay. So the site is in a midtown of Germany. It was a former military camp. You see that with these paved structures, the barracks, the military barracks you can see here. It's in the perimeter of a city close to a forest. Transforming a former military site in Europe is in the moment a very big thing, because you can densify cities. You're quite close to all the infrastructure facilities the city can provide. It's a plus. And it's not anymore in use. So, and we appreciated this approach very much. And our first consideration was, if that is the site, let's figure out what can we build there, maximum use of microclimatic conditions we find in the immediate proximity. How can we reuse what we find on site, and how can we maximize our carbon neutral or our microclimatic qualities back to the area. So wait a second, I have a technical issue. We started with a simple fact sheet. So we said, okay, let's base everything on a couple of aims, of targets. Optimized use of the microclimatic, I talked about, the choice of materials through a process of life cycle analysis. That was something we couldn't do ourselves. So we were happy that Thomas and his team and the university in Munich helped us to develop here criteria for designing an optimized building envelope, resulting in reduced consumption of materials. That's also something you can't do yourself as an architect. You have to have a good planner aside, and that was Thomas and his team, also energy consultants. Employment of natural and renewable building materials. It sounds simple, but it wasn't that simple. First, that's something Thomas will talk about in more detail, so I go over it. We look what kind of potential we find site, solar hours, geothermal potential, etc. And then we did a couple of different model approaches with all these criteria. Sorry, that was a bit too fast. With all these criteria embedded. And we finally ended with a very simple barn approach. So a simple structure which is orientated east-west, east-west. And that the reason for that was we wanted to have maximum north light. North light is a good light. It's an only light, less solar hits. The main issue for an area of working environment is always you have so many energy materials, you have the computers, you have a lot of heat gains in the building. So you want to have as little heat as possible, and you want to have maximum daylight in order not to turn on your artificial light easily. So a north light is good. Therefore, we cutted the roof. You can see that in this working model. We lifted the elements, the levels, to have a high level. The high level allows also to have maximum daylight hits in the depth of these plates, to have a little envelope with a maximum usage of square meters with high potential daylight conditions. The envelope or the big volume also helped to have lots of air inside. A huge air volume is something you can easily trigger in terms of stabilizing in the phases of cold and warm air situations throughout in the summer, for example. So it's a more stable air volume. So that was the first approach. And then we started together with Thomas, together with Thorsten, to work this conceptual diagrammatic architecture into detail. So we said, okay, we use from the close by forest in the western side, the air. A forest is a perfect clear or clean air venue. In the summer, the leaves provide shade, evaporation, it cools down the air. So we use that. And we suck in the air, we bring it to an air duct, and the air duct, you see that in the diagram on the bottom. We bring it to the inside of the building, and then we use the natural effect of a chimney effect in the atrium. What does that mean? The air is getting warmer, warm air rises up, and therefore we have a natural movement of fresh air brought into the building by no other means. So that was the air duct and the natural ventilation aspect. Then we said the south-orientated roof, perfect. We can use that for photovoltaic cells so that we can provide our own energy on site. Then we said we consume or we save and storage every square meter of water we can get on that facility. And we put that in an open lake on the south side of the building. The open lake helps to cool down the area further. Through evaporation, we can influence the microclimatic conditions, especially on the south side where we have a lot of solar gains usually. You see that the green part is getting very close to the house, so we get rid of paved structures as much as possible. Also a Bardo effect, so microclimatic enhancement by not having too much paved structures. We use water, and then we come to the heat. So we realized that this big volume helps very much to cool down the building in the summer, but it's getting too cold in the winter, so we need to heat the structure. And for the heat, we could use the geothermal on that site. We have the average temperature storage in the earth 10 meters below. The average temperature is roughly 10 or 12 degrees. So it's a very good stable heat we can use in summer to cool down and to enhance that with heat pumps in the winter to provide heat in the winter. When everything was sold, it came to the aspect, how do we build that? So now we have the structure, we have the barn, we have the light, we have the air. It came to what kind of materials we can use. And if you look on the left chart, you see that's a classical office section you have in every conventional office. You have the structure, you have a raised floor, you have a raised ceiling, you have a lot of layers in the facade. And it ends up that you provide only 2/3 of the construction materials to the people. 1/3 is only there to shape and provide technical elements which you need to install in the second ceiling or on the raised floors. It would be better to have a monolithic approach to provide every square meter you build to the users. That is the right chart. Simple roof, simple floor, a monolithic facade which should be durable. And this base and shell of everything is for me then the passive, simple room which could be in use for centuries, because whatever you install then in technical means could be redone, but the room itself is in human scale a usable room for the future. I believe that regardless what we have figured out by technical changes, that the demands of the people haven't changed tremendously. So the people are still looking for spaces which are having good daylight conditions, a nice view, perfect acoustical situations. The well-being of the people is a very stable aspect in architecture. So then we looked what kind of materials could help us to deal with this approach. And that is life cycle analysis we did with the University of Munich, where we checked various materials in embedded energy, efficiency during usages, and then the end of life scenario. Easy to say, it was not that easy. We put it roughly into various slides. We cutted the building and we checked the embedded energy factor and the life cycle in with different materials. Finally, we ended that using earth would be a great thing. Earth does have so much possibilities. It's available everywhere. It's a renewable resource. It's so simple. It was in use for centuries, but we completely forgot that we could reinstall that also in highly industrialized areas. When we started with rammed earth, with loam, I hadn't had a clue about loam. As an architect, I read a couple of books, but I was not informed in that way. So we were happy to, again, team up with an expert. That was Martin Rauch. You see the gray hair guy here on the top right image. And together with him, we had a year that was a lucky situation due of planning issues and approval issues to develop a couple of mock-ups to figure out, can we divide a kind of a rammed earth facade which would help to heat the building and which would be cost efficient and which would be durable and which would be allowed to be constructed on that site in a very short period. So what we did a couple of mock-ups. We checked, we knew that the pure wall wouldn't allow for good insulation. So we have to also produce a kind of an insulation inside the rammed earth facade. So we searched at the beginning, I don't have the English term for the Dinkelspelzen, that this element you see here in the basket. I think nobody knows the English translation. It's something, a crane, how shall I say? I send you afterwards what it is. So we checked a couple of materials, we searched for possibilities, how we can install a heating device in that wall. We came up for the insulation with a recycled material out of the glass industry. That's a kind of a glass gravel, which worked brilliantly together with a loam. And finally, we ended up with a production method on site. So we used the former barrack, former tank barrack for the loam earth brick production on site. And the innovation in that very old material was, it was finally completely engineered. because in that wall, you have a water piping system. The water pipes are connected to the heat pump and to the geothermal device. Therefore, we have a kind of a heating in that kind of rammed earth element embedded. You see the darker lines in that rammed earth. That's a lime and the truss different stone, which protects the loam against erosion. So it stops the speed of water coming down of that wall, and the erosion process could be treated differently with this kind of construction approach. We produced on site, you see the sizes of the elements, 3.5 meter, so roughly 10 feet by 70 centimeter, which is 20 feet. We needed to try them out for 3 months. We had a lot of discussions with the client about durability, and if you introduce a new material on site, every client asks you, do you have references? Is that something which is stable? Does it last for long? And luckily enough, there was a building in the Zoo of Bale where this kind of construction was west facing for 20 years, and we could look at it and we could see how tremendously nice erosion didn't harm this rammed earth blocks for 20 years. So that was the situation when the client was completely convinced. But the client was not an hindrance. He was someone who forced us to go into this area of a carbon neutral building, because Alnatura is in the organic food a big name here in Germany, and they very much liked to have a building which stimulates and helps and shares the way of thinking they have about everything, a holistic view about sustainability in the building itself. So they were also drivers and asked us to develop these kind of elements. You see that how it was then brought on site after 3 months of trying out. You could stack the 12-meter high columns of this rammed earth, little movie where you can see the big difference between the inside, because we said, okay, we have a shell. The shell should provide as much as possible shelter against sun, wind, water, but in the inside we want to have a freedom of space. We have a modern kind of working environment. On the roof, something Thorsten will tell you in more detail, we had a wood construction, 2 single wood elements not connected in the middle. And I need to say that these 2 wood elements were probably more sophisticated in designing than the rammed earth facade was, because that was not simple. You see the little columns, thanks to Thorsten and his team, something which was really which tremendously worked out nicely. And the building looks simple, but it wasn't simple in at all, because all the engineered elements you could not see. And the simplicity was something we wanted to have as a final result. But I have to tell you, that was a 2-year, really demanding run to come up with this kind of structure, because a lot of things were developed the first time in that building. Fire protection, everything was unsolved at the very beginning. So we had to deal with the authorities here in general quite heavily. I go over the wood roof. Thorsten, he's the expert. He will talk with you about the wood construction of that building in more detail, I guess. So allow me to go quite fast over it, because I also consume too much time. That is what I said, an emotional link to the people. They very appreciate the house. Now we have the 3rd summer where it is under use, and we had some harsh summers the last 2 or 3 years, so we can realize how easily that building works. The rammed earth is a perfect regulator for humidity It works acoustically. It provides such a nice air quality inside. It's a natural material people appreciate. So I think it was very much a success for the people working in, but also for the client himself. You see inside the last image I show before I hand over to Thomas, it's a different world, different in terms of it's not anymore that traditional, and we very much like this different aspect and the two different criteria of the house: a modern working environment with traditional materials, finally then in use as a carbon neutral building, hopefully. Lastly, I think you see the concrete here. The concrete, if you would need concrete or if you would need to produce the slabs in wood, that was a difficult question we treated ourselves quite often. And most likely, if I would rebuild again, or if I would redo it again, I would also construct the ceilings in wood. I think that is something we have learned out of this lesson of Alnatura, because something we also have learned is that energy consumption for transportation to bring all the goods to a site is a tremendous energy aspect which you need to deal with. And to have a really carbon neutral approach to buildings, you should build as much as possible regional from the site, and most likely not in concrete. Okay, Thomas, that's from my side. Thank you. I hope everybody's asleep.
Martin, maybe you stop sharing and I share, then I don't need to say next at every slide.
Good. Okay. So
we save some next.
Good.
Okay. So Martin already mentioned the energy strategy and talked a little bit about the context of the project. Let me in 2 slides or in 3 slides explain a little bit what we do at Transolar. So here, first of all, Transolar is an engineering firm. We're doing climate and energy strategies for buildings and districts. That's basically what we do, and mainly doing the computer modeling to inform a design process. So that's the basic idea. We got founded in Stuttgart, but we also have an office in Munich and an office in New York, pretty close to where you guys are, at Union Square, and a small office in Paris. Sounds like a big company. It's actually not. We are still a very small company of about 60-ish, 65 engineers. And then, as Thorsten has mentioned, since 2014, I'm also professor at the Technical University of Munich. Here, that's my staff at the university, the people, the research assistants mainly, as well as the secretary who support the chair. And I feel very privileged to be able to work in academia, doing research in academia, but also still involved in building design and doing projects at Transolar or with Transolar. 2050, Martin has talked about, I can jump over it. That's the European EU carbon roadmap. And so the European Union basically promised to the world that we're going to reduce our carbon emissions by 80% until 2050. That's where we are. The housing sector basically has to decarbonize in this strategy. So we not only new buildings, not only Alnatura, Martin has shown, basically the whole building stock. So if you look outside, everything you see should become decarbonized by 2050. That's a huge challenge. We don't know yet how to get there. There are different strategies. I think it's doable, but it requires a lot of research, a lot of effort, a lot of ambition. But I think it's changing our built environment to a certain extent. And that's why it's so important to get architects involved, because architects design our built environment. Don't give it up. Don't hand it over to the engineers. We might wake up in a world we don't want to live in, and in cities we don't want to live in. So it's a design task. We have to design it. And then Martin talked about this question of energy per square meter and energy per person. This is from a magazine where they said, welcome to the breathtaking Tokyo water park. And then below they stated, where you can wash away the pressure and stress of the overcrowded city, which is quite funny. But the energy consumption, like Martin has stated, per person is negligible no matter how much energy they use. And so we start to recognize that this question of decarbonization, this question of sustainability, we cannot disconnect from environmental quality, from architectural quality. We need to have places people love to go, people use. If we design a zero energy building or zero carbon building or energy plus building, whatever, however you want to label it, but people don't like it, people don't go there, people don't use it, then it's still a waste of resources. We still use materials. We still use rare materials. We still use land. So we can't disconnect it. It's all related. It's all connected. That's why we emphasize that it remains a design task, and architects have to get involved. You can't hand it over to some bloody engineers who have to solve it. So what do we do at Transolar? We call it climate engineering. So it has a lot to do with environmental quality, our work, and we got asked in 2010 to do an installation at the Architecture Biennale in Venice. And since we are usually dealing with what we call the invisible qualities of space, we thought that's quite boring. People go to a Biennale to see something and not to have something invisible. So we had this idea to do an indoor cloud. We did this a couple of years before at a fair in Frankfurt. So we said, let's do a cloud. And the idea of a cloud is you need to have a saturated layer of air. So you need to have air, let's say at 75, 80 degrees in Fahrenheit, and it has to have 100% humidity. Then it's saturated. And if it's saturated and you spray in water, the water cannot evaporate because the air is already saturated. And then the water particles remain in the air and become visible as a cloud. So we don't see humidity in air, we see water particles in air, condensed water particles. So now warm, humid air has a lower density than dry and cold air. So this layer of hot and humid, or warm and humid air floats on a layer which is cold and dry. And then in order to avoid that the cloud layer is touching the ceiling, because as soon as it's touching the ceiling, we would get condensation at the ceiling and the cloud disappears, then there is a layer of which is hot and dry above. So again, reducing density. So it's only a game of densities. We just reduce in every layer from bottom to the top, we reduce the density of air, and then we get the floating layers. The reality is a little more complicated. Let's say the physics remains the same, but in order to achieve these stable layers, took us a while. But at the end, this is how it looked like. Tetsuo Kondo, an architect from Japan, he designed the space, he designed the ramp where people could walk through the different layers and experience the cloud, experience the different temperature and humidity zones. And this, what happened? Here. And this is the cloud from above. So now it has nothing to do with our work in projects. We usually try to avoid getting clouds in buildings. However, it shows us to what extent we can really manipulate climate. We can manipulate environmental quality and really provide environmental quality where people are. And we really love this question of changing conditions because like you only enjoy warm if you come from cold. Only if you come from cold and you walk into a warm space, you say, this is nice and warm. Usually when you go from space A to space B at Cooper Union, you never walk in a space and you say, oh, what a nice climate. So it's this variation of conditions which makes people alert and creates a sense of well-being and thermal delight. We call it thermal delight. It's the same for daylight. And now coming back to this question of sustainability, and this is what we see right now in architecture. People apply gadgets to something which is stupid to begin with. And we have to get over this. We have to become much smarter in design, like the Alnatura building Martin has shown. So I'm going to jump very quickly because Martin has explained it in detail. So then we have some more time left for discussions. This is the climate analysis. So this is what we do. We look for hourly climate data to get a really good understanding of the local climate conditions, to see what are the challenges and what are the opportunities. So we look at temperature, at humidity, at solar radiation, at wind speed, at wind direction. So all these climate data, again, we have hourly from each location, and then we study those to get a better understanding of the strategies we can use. And this is the section Martin has basically shown already. So we do have this radiant system for heating and cooling embedded in this rammed earth wall. And we have a geothermal system below the building and a heat pump that provides the radiant heating and cooling in summer. Most importantly is that the building is based on natural ventilation, on passive cooling strategies, on humidity control of by the rammed earth walls. All these kind of passive design strategies, where all the mechanical systems you see here in this diagram are only supplemental. So we only use them during extreme seasons. All the exterior offices rely on natural ventilation. They open the window most time of the year for natural ventilation. What was very beneficial for the design for us was also that the client decided that there are no partition walls. So above the ground floor where all the offices are no partition walls. So we have 4 cores coming up, and in the center of the building, we just supply the air from the core. There is no horizontal distribution of air supply. So we have some displacement ventilation that comes out of this 4 cores. And again, the whole office is one open space, one room. It's a 1-room building, everything above ground floor. This is the rammed earth wall with the insulation you have seen already, and also in a section how it's integrated into the building. And here. This is the wall during construction. You see the piping we used for radiant heating and cooling purposes. Here in the center, you see a little bit these foam glass we used as a mineral material, as a natural mineral material for insulation purposes. And then the daylight study, where we could prove that with the skylight and the open character of this building, the atrium in the center, we get good daylight conditions throughout the building. And then here you see it already, you see it even in the pictures and the visuals, how good the daylight inside the building is. We did some monitoring. This was modeling showing that in all the different areas, we get decent comfort conditions. We do have some issues with BMS, with the building management system. But these are measurements we have made throughout a whole year. And you see in this different diagram, and I don't know, I'm not going to go into the details, but I want to focus on maybe 2 diagrams. Here is the one that shows in red the temperature outside, and then in green and blue, the 2 temperature zones where we have sensors, where we use the sensors in the inside. And one is pretty close to the eastern facade, to the western facade, to the western glass facade. And we had some issues with the BMS. And you see the gray here is indicating the comfort band. And you see in summer, we exceed the comfort band at a couple of days. That's when we had some issues with the shading controls. But you also see in wintertime that even in wintertime, we have still too high temperatures significantly in periods significantly above 20 degrees, sometimes going up to 26. So 20 is about 70, 26 is about 78. So it's let's say a bit too warm in wintertime. Now, what's interesting, I go to the next chart, and this is most interesting for us. I know we are engineering nerds, we love numbers every once in a while. But this is humidity, and it shows us how, to what extent material really controls humidity. In this case, we look at absolute humidity, or water content of the air. And the water content of the air we measure in gram water per kilogram of dry air. So I know you're used to thinking relative humidity, but relative humidity is a little hard to compare. So we love, as engineers, we love to look at water content. And you see again red outside and then blue and green inside. And here, for instance, you see those peaks and the gray band in which we want to stay to have good indoor relative humidity. And you see those peaks, how they are cut. So we take about 3 grams of water here at these peaks. The material takes about 3 grams of water per kilogram of air that goes into the building, that goes into the material. And then it goes out of the material at nighttime. And the same we see the other direction in winter time. We see here how dry it is in the outside air in a cold period. And we see the delta of about 2 grams that the material is contributing to the air, so that inside we could stay at 30% relative humidity. So with those diagrams here, you see as well, these deltas. This is coming from the rammed earth wall and how we can use material for controlling humidity. I mean, concrete is really great in controlling thermal comfort. Concrete is really good thermal mass, but it lacks a hygroscopic, let's say, behavior. It lacks, we don't get humidity in concrete fast enough. But it works really good in materials such as rammed earth. Rammed earth is the best. It also works really well with timber. Here again, some images of the building. Here the atria, I mean, you have seen those pictures. And then also, I think that's also something very important. It was measured in terms of indoor emissions, indoor carbon emissions, so-called VOCs, volatile organic compounds. Those volatile organic compounds are coming out of materials, of glues, for carpets, of paintings, but also out of furniture. And we did some measurements, or EE concept to be precise, did some measurements. And here you see that's the threshold which cannot be exceeded in accordance to the German green building rating system. And here you see in green what we have measured. So to what extent you can reduce VOCs, and people always talk about CO2 in indoor environments. Nobody cares about it. CO2 doesn't matter to people. We use CO2 as an indicator only. CO2 has no influence on well-being of people. What we recognize as bad air quality are odors. Odors mainly from people, but we can't measure odors, so we measure CO2. We only measure CO2 because we can. There's no reason in measuring CO2. But and odors is very, let's say, subjective, and people, let's say, human perception is the only sensor we have for odors, for air quality. So we should rely on human perception more than on sensoric. What's really critical in terms of healthy environments are VOCs. And here you see to what extent we can really reduce VOC emissions in our indoor environments. This is important because we believe that, not sure if you ever heard of sick building syndrome, we believe that VOCs do have a very close relation to sick building syndrome. So this is a big progress, very important. So, and then finally, talking about the rammed earth wall, we did, from the university, we got some research grants to really study on how much energy is going into a construction of a rammed earth wall. So we measured all the energy used, Martin Rauch has used on site, all the power that was going into this warehouse, but particularly all the trucks. And for a specific reason, the rammed earth, the material was coming from a 220 kilometer distance. And I make it very fast, but we compared it to a reference. And what we figured out is that this was during design, this was the result during design from a database, using data from a database. And we compared it also with another rammed earth building in Switzerland, for Ricola. And I jumped to the result, to the final result. Oh, no. Sorry. this is the final result. So what we figured out is that transportation of this rammed earth led to the fact that our wall at the end of the day is not any better in terms of embodied energy than compared, for instance, to an insulating brick wall. It has other properties which are beneficial, but in terms of embodied energy, we ended up that this transportation messed up our whole energy balance. And up until then, everybody thought about transportation being not that critical, actually. And we showed with this work, and it got published, that transportation is critical. And so the conclusion was that you can, a rammed earth wall, which is, let's say, now I remember, sorry for the confusion, the variant A is the Swiss building where they used the rammed earth from site, or the material, the earth they used from the site. And you see the comparison between the rammed earth facade and a reference facade. Whereas in our building, with the 220 kilometer transportation, we are worse than the reference. So a rammed earth wall is a really good material. It has a very high potential. Martin, how many people? I think it was 1 billion people worldwide who live, or almost 1 billion people worldwide who still live in buildings that are built out of rammed earth. It's a material we forgot. It has a huge potential, but when we compare it in terms of embodied energy, we have to make sure it's coming from the site, ideally, or from a place very close to the site. That's very important. I think that was the conclusion of this. Here you see again, even meeting rooms do not have partition walls, just curtains, and finally an image from the atria. That's it. Thank you.
Great. Thank you very much, Martin and Thomas. So before I open up for questions, I would just like to comment a bit on, like, I've learned how to design a cloud now. Thomas, thank you.
Yeah, it's not that complicated, isn't it?
Not that complicated, obviously. And yes, I like your, like you said, we designed the invisible quality of a space. So that's obviously not just the climate engineers, sometimes also the structure engineers do that, because most of the parts are invisible. And maybe, yeah, you have mentioned, and I think that's for rammed earth interesting, that like the hygroscopic quality of rammed earth to, let's say, control the humidity in a space is very important. And I know the story of Ricola, where they use it for the herbs, to store the herbs and control also the humidity. Okay, but it's not, I mean, I also like that the students learned about the sick building syndrome, and hopefully they also learn how to avoid this with their buildings. Okay, now, is there questions from the students? Or somebody else?
Nobody, so we are done.
Not the question. I may have missed it, but when you were talking about the results of the rammed earth building and its embodied energy, or energy that you said it was transportation, what's the difference? Like, do you have a chart or something that shows the difference, or quantitative difference between something, the same exact wall that was maybe without the transportation versus that exact wall with the transportation?
I mean, I could send Thorsten the paper we wrote, so he can distribute it. There it's described in more detail and depth. But again, when I quickly go back.
But also maybe you have to mention, Thomas, that the rammed earth used for Alnatura, and Alnatura, we haven't talked about this, Martin, I think. It's a bio, how would you say that? It's like Whole Foods, but maybe even more consequent, I would say, in how they use their products. So Alnatura has about, I think, I don't know how many stores in Germany and Austria. So it's
over 100.
Over 100 stores, and they sell only products from like certain, like they are controlled and so on. So they also wanted to make a building which kind of reflects their ambitions. And yeah, so I think that's maybe worth to mention. You probably have to mention, Thomas, that the rammed earth comes from the excavation of the railway station in Stuttgart, which is unfortunately 220 kilometers away. So that is why
I think, I think what we have to mention first is that when we started that rammed earth might be of benefit for the material, we also realized that Darmstadt is probably the worst place to start with a rammed earth building, because the ground there is more or less sandy, and we had difficulties to find in close proximity good rammed earth quality. And then it was more or less not by mistake, but it was a bit random to figure out that here excavation in Stuttgart produce a lot of garbage earth. They were looking for getting rid of it, and we could reuse it at least. But I think coming back to Thomas' chart, you can see it in the chart, the percentage of the embedded energy which is consumed by transportation. I think it's easily to read out of your chart if you compare it with the Ricola project.
So A is Ricola. Yeah. It's a little difficult because some of the, this whole life cycle analysis is, let's say, split up in phases. And so there's the A, the B, and the C phase. A is like until the building is built, it's like cradle to gate. B is the use phase, and C is the end of life phase. So we only looked at A, and A again is distinct. They differentiate between A1 to A5. And then it's, let's say, excavation of material, bringing the excavated material to the manufacturing hall, producing, for instance, a brick, and then transporting the brick to the site, and then construction on site. So those are the 5 phases. And for some of the phases we had data, some of the phases we did not have data. So that's why we can't separate for all the materials. Some of it is measured, some of it is calculated. That's what makes it a little, let's say, complicated to read out of the diagram. But again, like Martin has said, in variant A, which is Ricola, you see the potential of rammed earth if you take it from the site. So then you're this much better. And what was a little also amazed, where we were amazed about the result, was the fact that in our methodology of the Green Building Council, the DGMB, we don't consider transportation because it is assumed that transportation is less than 10%. And that transportation is for all materials about the same. And we figured out for a material like rammed earth, this is not true, because we have a 2.5 feet wide wall. If we do it in brick, it would only be a bit more than a foot wide. The material is super heavy, so it has a high density of something like concrete, of something like 2,500 kilograms per cubic meter. So we had so many more trucks that run to bring the material on site compared to a brick that we recognize for a material like rammed earth, which was totally unexpected for us and for everybody who is in this business. Transportation is critical, is crucial. And that's why we published it. And even the client loves the fact that we published it. I mean, nobody is criticizing that we did it, because let's say this is what research is about, is to create knowledge and to share this knowledge. And without this building, this knowledge would not be there. But here,
yeah, and I think that it becomes more and more an important aspect. We had a commission in Bremen, which is in north of Germany, for wood construction. And then they asked us, does it make sense to build here out of wood, because the closest forests are a bit more remote than in southern Germany. And then it comes to this aspect of transportation. And as Thomas said, the outcome of this research was that the aspect of transportation embedded in the technology in Germany is 9%, 9.5%, I think, in the Ökobaudat, something like that, and it's way higher. So every consideration right now where you talk about embedded energy is more or less based on wrong assumptions at the moment. So transportation matters. And that's also, we have another project, we were looking into a rammed earth construction in Hamburg. And the first thing that what we did there is we searched for close proximity of loam. So how far would loam be in distance from Hamburg? Would it make sense to build a rammed earth facade over there? As Thomas said, I think Alnatura for us, the innovation aspect of that was you have to start with something to learn about the values and about these aspects. And we were lucky enough to have a client which were reluctant and which were positive about the potential failures we could do with this kind of innovation. And the outcome of transportation comes to stupid situation. We had this situation with another client where we had a very nice material, but it was remote. And then the first thing we asked Mercedes-Benz if we could have electrified transportation. They have a truck, an electrified truck to reduce our energy consumption for that material. We failed. We didn't get that truck.
And we are in Stuttgart. You know, we should get such trucks. Anyways.
Yeah, absolutely.
If we can't get one, nobody can get one.
True. So next year you will design your first own project, right? Residential. That's going to be the spring semester of third year. So I will. I'm curious to see whether some will decide to use rammed earth or timber. So, but is there other questions from students or others? Not yet. Okay.
So we
good. I think there's a lot to digest, and I think what I will do probably in one of our next classes talk about the timber structure. We just started timber in our class. We talked about steel, but now started timber. So it's probably was too early to really go in all those details. But I think that having rammed earth and to learn about rammed earth from an architect and engineer, like from these two different perspectives, I think is very unique and was very interesting. And I would like to thank you very much, Martin and Thomas, for sharing your experience in working with the material and also in working together. As I also could, also join the team. I appreciate it. So thank you very much for Martin and Thomas for your lecture. Thank you.
Yeah, thank you, Thorsten, for inviting.
Thank
it was
you.
Nice to meet you guys, even if it was only virtual. But now it's well, how much? Almost 9:30 p.m. here. I think we have deserved to open a beer now.
Yeah, not the students. We have one more. We have the other half of the class too after a break.
I talked only 3 o'clock.
Talked only about Martin and me.
Okay.
Okay.
Thank you.
Thanks, everybody.